says. On the test, you see it says, consider the assembly below. Immediately says, this must be done with two parts, two bearings, left and right. Okay, I have to be more specific. Consider the assembly made of three parts in this case, and the shaft. Now, the bottom of this these bearings, they're identical. The bottoms are clamped, okay, welded against something else, and then the shaft is inserted there. That's very vague. What does that mean, inserted there? So we'll get to that in a minute. Somehow it doesn't move, just standard inserted there and stay there symmetrically. Okay. Now, I will apply a force to this shaft. Maybe I'll go and stand on it. Stand on it. The way it's described in the book and spelled out in the book is like this. Consider a downward load of 1,000 pounds applied to the surface of the shaft. There's no way that can be done. Because when you say 1,000 pounds on this shaft, the meaning of it, the way it's done in Catia, if you just go and select distributed load, select the shaft, it's going to put it there. But it takes every node, top, bottom, side. It puts, if there's 1,000 nodes, hypothetically, if there's 1,000 nodes there, you put 1,000 pounds. It takes 1,000 nodes and 1,000 pounds, 1 pound on each, on the top point, on the bottom point, on the points that actually inside of that hole. Inside of that hole, apply 1 pound at each location. You can't do that, okay? Think about it like this. Unless this is made of a magnetic material, you have a gigantic magnet there, it's pulling that steel towards it with a effective force of 1,000 pounds that electrical engineers can calculate. Okay, then it makes sense. But to do this problem in a meaningful way, not the way it's done in the book, this is from the book, I'll put a little stand in it, in the middle of the shaft, and I go and stand on that stand. Now that makes sense, as opposed to say the whole shaft is subjected to a load of 1,000 pounds. Okay, so that's one difference with the book. And in the book also, no planes of symmetry taken into consideration. So let me ask you this. If you look at this drawing, 1,000 pounds, it doesn't matter how I put on it, I'll stand in the middle, stand right on it, etc., or somehow 1,000 pounds on this whole thing. How many planes of symmetry do you see here? This is assuming that the shaft does not slide back and forth, because if it slides back and forth, I can't even run it. But if that is not the case, how many planes of symmetry do you see? Yes. Can you tell me how? Which two? Yeah. I mean, at least point it to me. Or usually I put coordinate system here, but I didn't do it here. Length. Yes. So one is along the 10-inch length, okay, and the other one is perpendicular, halfway between the two shafts. Just cut it between the two bearings. Just cut the shaft like that. You're right. And this is correct. But when I do a problem later on, I will show you that depending on what else do you say, one of those planes may be gone. Okay, one of those planes may be gone. And we will have to say something else, because remember I said here, pretend that this can stay there without actually moving sideways, okay? And this can in real life happen because of the friction between the shaft and the hole. Because of the friction between the shaft and the hole, it won't let it go sideways, okay? But we will get to that in a minute. Okay, so I will not use any planes of symmetry for this round. Maybe on Thursday we do it, or on videos that you're going to watch. So let's go ahead and make it. I'm going to ignore all the dimensions here. So I'll make something, roughly like that. I go here, and notice that I'm starting in product. In the past 3 weeks, as soon as this thing popped up by default, I close it. Because I said that we're dealing with a single part. Let's not confuse ourselves and do product. But now we have no choice. We'll have to do it as product, which is made of 3 parts. The other thing is that my approach to these problems, these are simple, basic problems. So I will make the parts in front of my eyes. As I move along in this product, I make the shaft, then I make the left bearing, then I make the right bearing, okay? But in real life, you know, this doesn't work because maybe left bearing is done in Winnipeg and right bearing or the shaft is made in Vancouver, okay? And the guy who works on it there, he doesn't care about what you do. He has a part and models it and does whatever with it, okay? But we're not going to do that. I'm not going to create 3 parts and then bring them into product. I'm going to do it while I am in the product. Okay, here's a product file. The first thing I'm going to do, I'm going to save this product. So we go File, Save Management, Save As, Desktop, New Folder, 10 a.m., 10 a.m. class, 10 a.m., 10 a.m. So everything that I do with you guys is going to go into this. Okay, so I'm going to insert my first part. And what I do by that, insert, new part, in there, part 1. And I'm going to name this thing, right-click properties. Since I decided to make the shaft first, let me, notice there's 2 things here. One is saying instance name, the other one is the part name. First of all, Catia does not, part number. Catia does not have part names, it has part number. So if I change this thing to shaft, for example, what happens, let me say, okay, apply. Okay, notice that when I put the shaft here, the part name changed, but this guy stays as part 1.1 because this is the instance name. If you want, you can make this thing also shaft, and then both of these. The first one referring to the part, the second one referring to the instance of it. I'll worry about instance later on. Right now, it doesn't matter to us. We're going to make it. Double click on the shaft. We go to the part design. On that face, on that vertical plane, YZ plane, I will sketch. The shaft, I make it radius 0.5. So 0.5. Okay. Exit. And let's say it's 10 inches long. So 5 inches in each direction. So I'm going to do a pad, mirror extent, 5 inches in each direction. That gives you a total distance of 10 inches. This is going to be my shaft, except that I want to put a stand on it, okay? Because we will put the load on that stand instead of this thing that's in the book. So on this horizontal plane, I will sketch, I don't know, maybe some circle, exit. You could have done, you know, rectangle, could have been a rectangular patch, it doesn't matter. And then I'm going to pad this. I'm going to make this thing maybe 1.5. 1.5. There, I'll put my load on that. Okay, that makes sense this way. Good. So this is done. Click on the product and just click on the floppy. Because when you do that, the product has already been saved. The very first thing that I did is save the product. The part I didn't change, but this way of doing it is take this part, put it in that same folder, and updates everything. Okay, so we say, just click on the floppy. If you put this thing on the top level assembly and click on the floppy, it will not ask any weird questions, where and what and things like that. It goes to that folder and puts this shaft there. Now I'm going to insert my second part. Insert, new part. It's a good idea, at least once in your life, read this thing. I'll let you do that. Or say no, I always say no. Start thinking about this new part that you want to put in there. Do you want to have the same coordinate system as the first one or a new one? I said always the same coordinate system. Okay. And let's change this thing, call it bearing. Right click properties. This is the instance name, bearing. And this is the part name, bearing. If for some reason you want different things, feel free to do that. And now we're going to make it. So you double click on the bearing. We are in part design. We can make the bearing. And I'm going to let that go in front of me. I can see it so that relative wise I can see how big things are. Now, the bearing, I have choices. I can make it on this sketch, draw something that looks like that bearing and then pad it. That's one way. Or I can draw it on the YZ plane, just like I did this one, draw something and pad it. The only thing is that if I go that route, and I will go that route, is that this is not going to be at the right location. You have to move it and put it in the right place by using assembly constraints. Okay? And that's what I'm going to do. So on this vertical plane, I will sketch. All right, I want to sketch a hole exactly the same size. So I can draw a circle and then, dimension it, etc. Or I say, I'm too lazy to do that. Why don't you project that face, that circle into that? See that? There's the project icon. Project this, and it just projected it on that YZ plane. Now, it is yellow because it's the outcome of projection. You cannot change the size of that circle, for example, because it's projected from something else. If you want to make changes like that, and I don't want to, okay? But if you ever want to do changes like that, that yellow thing that you projected, if you put the cursor on it, right-click, you can say isolate. Oops. You can say isolate. Notice the color yellow goes away. And when the color yellow goes away, you can actually move things around. You can dimension it, etc. It doesn't matter to me. I just wanted to show you. Worst come to worst, draw the circle, dimension. Okay. And let me do the rest of the problem. Now, if this is bothering you, you can hide it, right-click hide, or if it's not bothering you, just go ahead and do the rest of the bearing. So here's what I'm going to do, something like this. Okay, I'm not going to worry about dimensions. Exit, and pad it in each direction by, how about 0.5? 0.5. There, this is my bearing. And the reason it looks weird like that, because I used the YZ plane to make my sketch and padded it, so eventually I have to move this thing. Now, we want to save this. So I go to the top level, click on the floppy, and it's going to save the new stuff. Now, the other bearing is exactly like that. There's two bearings and one shaft. The other bearing is exactly like that, and you have several choices. You can go through this process, right-click, insert, where am I? Insert, new part, just like I did with the bearing. New part, and then go make it. You can do that one way. The other option is, because these look exactly the same, is right-click, copy, go put it in the bearing, paste. Notice that what happened is that I had the original bearing that I made here, and there is a copy of it down here, identical. The alternative would have been insert existing component. You see that? Insert existing component. And I can do this and then grab that bearing that I put in the folder and bring it in. It will look, the tree will look exactly the same. There's going to be a bearing and bearing, but there's a big difference between them. It does not take hard disk space, because if you had 1,000 bearings, 1,000 bolts, that's not uncommon, and you wanted to model a copy of every bolt, for some reason you wanted to model every bolt, then every single bolt that you copy and paste, or a new part that you make, every bolt 1, bolt 2, bolt 3, they take disk space and resources. But if you insert existing component, it will not actually take disk space. Disk space is only for that original one in the instance, okay? These other ones, you can bring it in and you can use it, analyze it, but they don't take any space. But I didn't do that. Copy and paste. On a homework or on the test, do whatever you want. Just do the problem. Okay. As a matter of fact, if this had two planes of symmetry, I don't even necessarily have to make the other piece if you don't want to, if you know that you're on the right track and you just need one of the bearings because the plane is symmetry, just make one of them. No, that's not what I did. Now, let's, first of all, before I go any further and I move these apart, because I have to put them in the right spot. If they all have the same properties, everything is made out of steel, you can put it on the assembly, it automatically puts it on every part. But if the part shaft, for example, is made of steel, the bearings are made of aluminum, then you have to go individual parts and apply material to it, okay? By putting it on the assembly, it's going to apply to all parts. If there are different type of materials for these different parts that you have in your problem, you go to that part and apply material to it, just like you did the other 3 weeks. I'm going to put steel on everything. So at the top level, I'm at the top level. Double gear means that you're at the top level, you're at the assembly level, and you go apply material. You have done this thing many times. It's the same icon. Let's say metal, steel, and then on the part, of course, it's going to be okay. And this is going to go on all 3 parts. Now comes the issue of putting these in the right spot. You know, I don't care how you do it or what you do it, you got to give me something like this. So let me show you how I would approach it. All right. There, you're in the assembly design, and these are the constraints that you can put in assembly design. First thing, and I neglected to do this with the first group, but here I told them about it. When you try to assemble stuff, you better, to begin with, fix something. For example, let's hypothetically say, I want to put this chair next to that chair. I can select this chair and I can select that chair and say coincidence, and they're going to go together. But I don't know where they're going to go together, whether that guy is going to come here or whether this guy is going to go there. If that happens to be a source of confusion, always fix something. Fix that guy, for example, and in Catia's assembly is called anchor. Fix something and then move stuff relative to it. At the end of the day, you have to do this properly. I don't care how you do it, okay? So let me fix the shaft. Here's the anchor, and it says go pick it. Now the anchor will not move. The anchor or the shaft will not move. Other stuff will move, but not this guy. So coincidence, you see that? There's the icon coincidence. You're going to be using this thing for the rest of the semester, even after the break. After the midterm, you're going to be using a lot of the stuff. You say coincidence between this plane and that plane. These arrows mean something, but for now, let me ignore it first. Say OK and say update. There, one of them moved. And I do the same thing to the other guy. So coincidence between this face and that face. Now, if I do that, update, you see, it didn't quite do because I should have selected maybe that face. But there are always ways to sometimes to salvage these things. For example, if you go to a constraint, let me see, where is this? There's your constraint. When I double click on this, these arrows pop up. These arrows mean something. So let me click on it, flip it. Remember, they were pointing in the same direction. And now update and see what happens. Okay. Now, you have to turn this thing. And it's very easy to do. But it takes practice. So what I'm going to do, one way of doing it. There's a zillion ways of doing these things. First, I'm going to rotate this bearing so that it's more in line with what I want, and then put 2 coincidences between 2 faces. That's the way I'm going to go. So I'm going to go to this icon is my favorite one, move, manipulate. You can also do it with compass. I don't like to do it with compass. So there is the move. The first one is move and manipulate. I'm going to rotate this thing about the x-axis. These are translation. These are rotations about different coordinate system, x-axis. So I drag it until I'm happy. And now put a constraint. Because sometimes these are far apart from each other, and you do constraints things happen, and then you have to go fix it. Coincidence between, for example, this plane and that plane. He turns it a little bit. Okay, well, I was pretty close to it. Very good. And don't forget to save in case the power is lost, your computer crashes. At least everything up to this point has been done. All right. So, move on. By the way, before I move on, I have not put enough assembly constraints on the structure so that it always looks like that. Believe me, let me show you. I can take, for example, look, I can take this guy, this shaft. Let me take this shaft, okay, and rotate it about the x-axis. And it's an update. So that one must be okay. Maybe I have put enough constraints, I'm not sure. But if you have not, when you move things around and then you think that, oh, I'm going to update it, it goes back to the original position that I wanted, it may not, because there may not be enough constraint. It looks like I had it here. Don't worry about it. This is not very critical in this portion of the course, but after the midterm, it's completely different ball game. Okay, but move on. So we go to generative structure analysis. You click on it. Catia immediately sees 3 parts, and it gives 3 meshes. Static analysis, of course. Where's my tree? Where's my tree? There, F3. Catia sees 3 parts and immediately mesh 3 of them. Now, by the way, anything that you don't like, these O's that you see here, these are coming from the assembly constraints. If you don't want, you can go and hide these guys. Like I can go back to assembly back here. Anything that I did not like and it's bothering me, I'm going to hide it. Constraints. Right click, hide, gone. Any planes that you don't want to see, you can hide it, not 12 times or 9 times here, but you can select all the planes at the same time and hide every plane. So if you want to see that, I'll show you later. You have to search for all the planes, select them, and then hide all of them. Because if there are 50 planes, you're not going to do it one by one. But that's okay. I'll leave these planes here. Let's go back to the analysis. Right there. Now, first of all, would you say that this mesh for the shaft, because Catia looks at the size of the object, and based on the size of the object, comes up with the size of the element, which is a poor strategy. But if I'm sure you're going to say, wait a minute, that is too big. But give me a reason why it is too big. See, on the shaft, one on this side, one on that side, I can live with it. But for that particular shaft, I don't like that. But I want a reason for why. And let me give you typical questions. Same question. Why is that too big for this problem? Part A, because they're all the same material. Part B, because shaft is bigger than the bearing. Stuff like that. I want you to give me the correct answer. Part C. What is the correct answer?
Most of the force and the stress is going to be in that radius.
And you're right.
Too big compared to the radius.
You mean the radius of the shaft or radius of this? Oh, okay. So let me ask you this. If this stand was not there, if that stand was not there, and the problem was just shaft between the 2 bearings, and you apply somehow a load of 1,000 pounds, where would the biggest stress be? Yeah. That is a possibility. That is a possibility, but it's also the middle of the shaft, because the middle of the shaft is at the biggest deflection. The biggest deflection. Biggest deflection means the biggest stress. Here, the situation is even more dramatic because I have this stand with a 90-degree cut, no fillets there. So stress concentration even takes those bigger stresses and multiplies it by stress concentration factor. It's even worse. In other words, the colors are very closely packed around that seam on the shaft and the stand. Being very quite packed there, that means that there's a stress concentration there and colors change very rapidly. If I have a gigantic element there, those colors cannot even come within one element. The moral story is that because of the stress concentration of that non-filleted object in the middle, you have to take definitely much smaller element than that. Now you can, of course, you can go ahead and make a local mesh refinement. You can do that. For example, look. I can do the same stuff that we did before. For example, local, where's that? Local mesh, remember that? You click on it, and it's going to say, okay, it's going to pause here. Because if you read the bottom left corner, it says, all right, you want to refine, but which elements? Because there are 3 elements here. It never asked this before because we never had a situation with there were 3 parts. Here it says which part I want. Obviously, it's not quite the which part, it's which element. So if you look at your tree, of these 3, which one is it that you want to refine? It's this one. And then it says where? Which one of these? And now that you decided which one, where? Obviously, I want to do it around the seam. Now, if this may be too big, I'll make it 0.2. Okay? You say, okay? This is more civilized than making it everywhere small. I could have made this gigantic element here small everywhere. I could have, but there's no need to do it in these locations. So right-click, mesh visualization. You see? Anything that I don't like, I can hide right there. At least there's some hope of resolving that stress gradient around that seam with these elements, but there was none before. I didn't show this thing to the first group, but I told them, but we did everything small. Okay, deactivate this. Yep. All right. So the bottoms clamped. Clamp this and clamp that. And put a force of 1,000 pounds on that stand. And it knows it from earlier this morning. That's why I don't have to change it, minus 1,000. And I'm going to run it and watch it fail. Good. And then pray that Catia can give you an idea what the issue is. You click on this deformation. There we are, and animate it, and you can see what the problem is. That the shaft has no idea that there is a bearing there holding it. It just goes through it. So we have to create a connection between. Connection means tell software that the shaft is related to the hole. It doesn't say what kind of relationship, siblings, friends, enemies, just related, and then declare the type of relationship. Now, you know how to do the connection. You click on the connection, face of the shaft, face of the hole, you create the connection. Let me do that for you. First, we have to deactivate. Remember, with this guy in front of you, there's nothing you can do. It's going to happen over and over and over. I can't do this, I can't do that, because you're looking at an image, basically. Connection, we have done this thing. Face of the shaft, and for the second component, hide the shaft, because I want to select the face of the hole. And it puts this connection thing in between them. Centroid of the shaft, centroid of the hole, puts 2 dots there connected with the red line. You may not see the red line in another problem because these 2 points may be on top of each other. So you just see one big dot. Now, let me do one on this side. This is why it's a good idea to call these things names. For example, left bearing and the shaft, the right bearing and the shaft. The next one is going to be right bearing and the shaft. This one, I'm not doing what I'm preaching. So for the second component, select the whole. The order is not important. Okay, so let's bring this thing in the show so that you can see that. I created two connections right there, left bearing, right bearing. Now, you have to be very careful here. If the problem statement says that these parts, shaft and the bearing, are perfectly bonded, perfectly glued, perfectly welded, as if this part was machined like that. When you think about it, if these are perfectly bonded together, it's the same material, it's just like spending thousands of dollars trying to machine a part like that. It's not three parts. So I could have solved this thing as a part problem, actually. Don't do it. If the problem is an assembly, you must solve it as an assembly. But if it says these are perfectly bonded, perfectly good, okay, do it as an assembly, but declare this connection as fastened. Fastened. That essentially becomes one part. If it doesn't say these are perfectly bonded, perfectly glued, perfectly whatever, then means that you can put the shaft in there and then you can take it out. You know, it's basically a contact problem. You cannot penetrate it. Okay. If I declare that as fastened, it would not have penetrated anyways, because as it was moving, the hole would go with it, because these are essentially one part. But let's do it as contact. So here is a contact. The third one is fasten. We have done it. Contact. And you can do it from the tree. Notice that the icon for contact is, you can see, hard to see, instead of a fastener sign, it's two plates on top of each other, two rectangles on top of each other. You can see that inside of that big red box. And the same thing. Do not fool around with these things. Leave these alone. If you want to know what they are, I'll be glad to discuss it with you. With this course, do not fool around with these, please. That's because if you do and you get something that you didn't mean it, but it came out wrong, then you lose the part for that particular, issue. Another one over here, another contact for this other guy. It puts the same thing on this side. You see that? And we're gonna run it and watch it fail again. I'll be done in about 2-3 minutes. Definitely, we're not going to be doing the cuts. Okay, it didn't work. So what happened? So let's look at the deformation. Can I animate it to see, maybe give me an idea? Can you see it? Okay, if you can't see it, if you can't see it moving, let me change the scale a little bit, maybe 10 times bigger. Make this thing 9. Okay, now you can see it properly. It can no longer penetrate the bearing, but it can slide in it. Nothing stops it from sliding. I have to take away that. The question is how? I have to give you instructions on how to do that. For example, I might say, take the edge of the shaft and the edge of the hole, make them perfectly bonded or perfectly welded or fastened. That's one instruction. I can say that take the edge of the shaft and the edge of the hole on this side, edge of the shaft and edge of the hole on the other side, perfectly bonded. This is also the same thing. But the second one, this middle one, is a plane of symmetry. With the first one, on this side they're welded, on that side it's not, then that plane is not a plane of symmetry. There is one along the beam, along the structure, but not perpendicular to it. I'll do only one side. Okay, I'll do only one side. So so the instruction to you is this. The edge of the shaft and the edge of the hole are perfectly bonded or welded. etc. So let me deactivate this. Okay, so let's do that. Create another connection. Now you can see these number of connections become large, and you may be not doing yourself a good favor by giving these meaningful names. So let me hide this. So for the first component, I select the edge of the shaft, like that. And for the second component, I select the edge of the hole, the right edge, of the correct edge, not the other edge, the one in the back of it. And then I say this last one is fastened. So look for the fastened. The second one was contact, third one was fasten. Fasten you have seen in class, and it's this last one. Notice it does put the fastener sign right there. Okay. In fact, if you want to see where the other bearing is, I put it in hiding. Let's bring it up. Right there. And we say okay. And we're going to run it. You see that this time it will run, but let's watch the other side. Well, let's watch the other bearing, see what happens on the other side. Okay, good. So let's look at the displacement. Change it to average ISO, material shading, so that we can see better. I want to turn this thing a little bit around. Come on. This tells you that I have a problem with this performance of this guy on my computer now. Maybe I use this. Okay, so let me animate it. The other side, the edges were welded together. This side, it's not. Look, it's coming out of the hole. It'll be coming out of the hole. It is. It is coming out of that hole. That's because it's left free. It just slides out. This is why there is no vertical plane of symmetry to this. There is one along the axis. And if you look at the von Mises stress, just like what we expect, there's going to be spots here. See that? And there's going to be spots at the end because of what you were saying. In other words, the shaft actually on this bearing, it's going to bend it, and at the edge, there's going to be some color. You can see that right there. So both of these important, but the question is for your design, what are you designing for? Are you worried about the bearing, or are you worried about the failure of this thing in the middle? Then you concentrate on your stuff.